4 humans just watched the first solar eclipse ever seen from behind the moon. And while they were watching, meteoroids started slamming into the moon. Not 1 impact, not 2, 5 or 6 in a single hour. Kiloton-scale detonations, live, in front of them. And now those same 4 people are pointed at Earth, flying home through the same region they just watched get hammered, with a heat shield that has a failed test behind it, an 18-day radiation streak cooked into their spacecraft, a sun that fired a near X-class flare at them with 0 warning, and an asteroid closing in closer than the moon itself. The next 72 hours are either the greatest moment in human spaceflight history, or the most important cautionary tale we never saw coming. Stay with me. Every single minute of this matters. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as this story unfolds. Drop a comment with where you are tuning in from, what time it is there, and tell me this. Did NASA make every reasonable call with the information they had, and the universe simply decided to stress test all of it at once? Or are there harder questions that nobody in that press room is willing to ask out loud? Part 1. The hour that shouldn't exist. 5 astronauts have ever travelled beyond low Earth orbit and lived to describe it. 4 of them went to the moon. The 5th almost didn't come back. And now, for the first time in over 50 years, humans are out there again, and what they just witnessed in the last few hours may be the most important thing any human being has ever seen from space. Not because it was beautiful, though apparently it was stunning in a way that no photograph will ever fully capture, but because it might be a warning. A warning delivered by the universe in the most spectacular way it knows how, by lighting up the darkness with explosions. Let's start at the beginning, because the beginning of this story is unlike any beginning in the history of human exploration. On April 6, 2026, the crew of Artemis II positioned their Orion capsule on the far side of the moon, completing the most distant crewed trajectory in human history, farther out than Apollo 13's unintended record, sitting at roughly 4,067 miles beyond the lunar surface. To understand how far that is, consider that the moon itself is about 2,160 miles in diameter. The crew was not just near the moon. They were 2 full lunar diameters beyond it, on the side that faces away from Earth, in a place where no human being has ever physically been. Ever. In the entire 200,000-year history of our species walking this planet and looking up at the sky, not one person had ever been where those 4 crew members were on April 6th. And from that position, something occurred that no human being had ever witnessed before. The sun disappeared behind the moon. They watched a solar eclipse from the other side. Not from the surface, not from low orbit. From a vantage point behind the moon, looking sunward, watching our star slide behind the lunar disk, from a perspective that no camera, no probe, no robotic mission has ever captured with human eyes present to experience it. The corona, that faint, impossibly structured halo of superheated plasma that surrounds our star and is normally invisible in daylight, stretched outward in every direction, extending several solar diameters into the surrounding black. Streamers and plumes reaching millions of miles into space, visible in full detail because the disk of the sun was completely blocked. Below the capsule, faint earthshine painted the lunar surface in a cold blue glow, light reflected from Earth, bouncing off the moon, travelling back toward the crew, illuminating the grey regolith in a way that made the dark, unlit surface faintly, hauntingly visible. 4 human beings floated in silence and watched the universe perform a trick it had been rehearsing for 4.5 billion years with no audience. And then the surface started exploding. Not metaphorically, not atmospherically, not in some distant, abstracted astrophysical sense. The moon, lit up in eclipse geometry in a way it has never been lit for human observers before, began showing flashes. Reed Wiseman and Victor Glover, watching from the capsule, reported 5 to 6 distinct impact events within approximately 1 hour. Meteoroids, chunks of rock and metal moving at velocities that make rifle bullets look leisurely, that make artillery shells look like they are being thrown by hand, were hitting the lunar surface in real time, while they watched, while they were close enough to see it happen. Because the moon has no atmosphere, there is no ablation. On Earth, when a meteoroid enters the atmosphere, friction with the air converts most of its kinetic energy into heat and light spread across a long, luminous trail across the sky. The energy is distributed, The object usually disintegrates long before it reaches the surface. The Moon offers none of that mercy. There is no atmosphere. There is no friction. There is no distribution of energy across a path through the sky. The entire kinetic energy of each impacting object gets delivered instantly, completely, catastrophically to a single point on the surface. The math on those events is worth sitting with for a moment. Even a relatively modest meteoroid, something the size of a large grapefruit, nothing that would make headlines if it hit Earth's atmosphere, moving at 20 kilometers per second produces an energy release measurable in kilotons upon lunar impact, not kilotons as a figure of speech, not kilotons as a poetic exaggeration, kilotons as in the unit we use to classify nuclear weapons. The flashes the crew watched, those brief, stark points of light on a grey surface, each represented an explosion that would have levelled an entire city block. Now here is where you need to sit with something genuinely uncomfortable for a moment. NASA's Lunar Impact Monitoring Program, run from Earth, using dedicated telescopes, staffed by scientists whose specific job is catching exactly this kind of event, confirms roughly 20 impacts per year from ground-based observation. 20 per year, less than 2 per month. The Artemis II crew witnessed 5 or 6 in a single hour. You can immediately raise the objection that proximity helps. They were right there. The lighting was perfect. The eclipse geometry made the unlit surface more visible than it ever is from Earth. And all of those things are true. Observational bias is real. You see more when you're closer. You see more when conditions favour detection. And the conditions during an eclipse on the far side of the Moon are, by any measure, extraordinarily favourable for detecting impacts. But even after you account for every observational advantage, even after you apply the most conservative bias correction you can reasonably defend, even after you give every possible charitable interpretation to the baseline comparison, the observed rate in that 1 hour appears elevated. Not slightly. Not at the edge of statistical ambiguity. By a lot. And the crew knew something was unusual. Their reported reaction was described as giddy. Giddy. These are trained mission specialists, people who have spent years constructing the psychological architecture to remain measured and professional during high-stakes situations, people who do not generally respond to routine observations with giddiness. And they were giddy. There is something almost unbearably human about that detail, because giddy is what happens when 2 competing responses activate simultaneously. The part of the brain that says this is the most incredible thing I've ever seen, and the part that says this is not normal. Both of those responses were correct. The wonder and the unease occupying the same moment, in the same 4 people, in the most remote location any human being has ever occupied. But here is what transforms this from a remarkable observation into something with operational consequences. In the first quarter of 2026, ground-based fireball detection networks registered an anomaly completely independent of anything the Artemis II crew observed. The American Meteor Society data showed an increase in reported fireball events, roughly 4.5 standard deviations above the historical average for that period. 4.5 sigma. If you have any background in statistics, you know what that number means. 3 sigma events are considered significant enough to publish. 4 sigma events make people request independent replication before they believe what they are seeing. 4.5 sigma is the kind of deviation that makes researchers stop mid-sentence and go back to their raw data to check for errors, because the alternative, that something real is happening, seems too significant to accept without extraordinary verification. This data came from Earth, filtered through our atmosphere, which absorbs and disperses a significant fraction of the incoming debris environment before it ever reaches the surface. Small objects burn up completely, medium objects fragment and spread their energy across the atmosphere before any ground sensor detects them. The Moon has no such filter. It receives the full, unmodified, unattenuated, completely raw input of whatever is moving through near-Earth space. If the fireball rate on Earth was running 4.5 sigma above average, what the Moon sees is everything the atmosphere stripped out before Earth's detectors ever had a chance. The Moon is the cleanest sensor we have for the true state of the near-Earth debris environment, and what the Artemis II crew watched on that sensor, live, with their eyes, from 4,000 miles away, was not consistent with normal background rates. No official body has confirmed a systemic increase in debris density. That statement matters and cannot be glossed over. This is not a confirmed crisis. The alternative explanations, pure observational bias from the crew's exceptional detection conditions, coincidence, a transient and localized debris stream that the capsule trajectory happened to pass near, an unknown comet or asteroid breakup event that has not yet been identified, are all live, scientifically legitimate hypotheses. But the convergence of two independent data sources, one from Earth's detection networks and one from 4 human beings sitting 4,000 miles beyond the Moon, both pointing in the same direction at roughly the same time, is not something you explain away with a footnote. It is a data point that demands an answer, and right now we do not have one, because those 4 human beings are now heading home, and the path home goes through exactly the region they just watched getting repeatedly, energetically, visibly hit. The April 6th lunar flyby was the turning point of the mission in every sense. The trajectory of Artemis II is what mission planners call a free return path, a gravity-assisted arc that loops around the Moon and uses the geometry of the Earth-Moon-Sun system to redirect the spacecraft back toward Earth without requiring sustained main engine propulsion. It is elegant engineering. It is the kind of solution that reflects the best of human ingenuity applied to orbital mechanics. It is also an absolute constraint. The crew cannot hit a button and accelerate their return. They cannot trade fuel for time and arrive home earlier. They cannot meaningfully alter the timing of their approach to Earth. The arc is set. The physics owns the schedule. Between April 7th and April 10th, they are committed to a 72-hour transit through the environment they just watched from the far side of the Moon, outside the protection of Earth's magnetosphere, exposed to the full radiation environment of interplanetary space, flying through a debris field that their own observations suggest may be running hotter than the models predicted, and heading toward a re-entry that has never been tested with people inside it. Nothing has failed yet. No alarm is sounding. No system is in distress. The crew is healthy, the capsule is intact, and the trajectory is exactly where it's supposed to be, but everything around them is active. The sun is active. The debris environment is active. The electron flux that has been saturating their spacecraft for 18 days is active, and they are committed to a path through an environment that changed, or more precisely revealed itself after they left Earth. The question is not whether we built a capable spacecraft. The question is whether we built it for the environment that actually exists out there, not the environment that the models predicted, and we have exactly 72 hours to find out. Part 2. The first off-world confirmation. Before we move into the radiation environment, it is worth staying with the debris picture for one more moment, because the scientific significance of what the Artemis II crew observed extends well beyond the immediate risk to their mission. What they witnessed is potentially the first off-world corroboration of an anomaly that researchers on Earth have been watching build since January of 2026, and the implications of that corroboration stretch far beyond this single mission. Earth-based detection of the near-space debris environment is inherently limited. Our atmosphere is an extraordinary filter. It vaporizes the vast majority of incoming material before any instrument on the ground ever detects it. What survives to produce a fireball visible to human observers or detection networks is a relatively small fraction of what actually enters the atmosphere. The objects that burn up silently, invisibly, at altitude, they never appear in any dataset. The American Meteor Society fireball anomaly in Q1 2026 is derived from objects large enough and energetic enough to produce visible light through atmospheric ablation. The true number of objects entering the atmosphere during that period, including all the ones that were completely vaporized without a trace, was almost certainly higher, potentially much higher. The Moon strips away that uncertainty. Lunar impact monitoring programs operate on the principle that the Moon receives the same debris environment as Earth, but without any of the atmospheric filtering. What hits the Moon is the true input signal. The rate of lunar impacts properly measured is one of the cleanest available proxies for the actual density of the near-Earth debris environment. For decades, this monitoring has been done from Earth, using sensitive optical telescopes watching the lunar night side for the brief flashes of impact events. The program works. It has produced a baseline, and that baseline says roughly 20 confirmed impacts per year. What the Artemis II crew saw in 1 hour does not fit that baseline, even generously corrected for their detection advantages. And this is where the scientific value of human presence in deep space becomes not abstract but concrete. No robotic probe in lunar orbit would have been watching the surface with human attention during that eclipse. No automated system was positioned to capture the subjective continuity of the observation. The fact that two trained observers watched the same surface continuously, without breaks or pointing adjustments, and counted what they saw. The data the crew brought back from that hour is not perfectly calibrated. It is not a controlled scientific measurement, but it is real, independent, off-world evidence that is consistent with the ground-based anomaly. The two data sources did not talk to each other. They just agreed. What could cause elevated debris density in near-Earth space? The honest answer is that we do not know, and anyone who tells you confidently otherwise is either more informed than every published source on this topic, or is guessing. The known mechanisms include comet breakup events, a comet entering the inner solar system and fragmenting, leaving behind a debris trail that Earth and Moon subsequently pass through. This has happened before. The comet Biela fragmentation in the 19th century produced the extraordinary Andromedid meteor storms of 1872 and 1885, with rates so high that witnesses described the sky as raining fire. It can happen again. Whether it is happening now is unknown. Another possibility is a recent asteroid disruption, a small asteroid fragmented by a collision or by tidal forces during a close Earth approach, producing a population of smaller objects that have not yet been catalogued. Asteroid disruption events are not rare on geological timescales, but identifying the remnant debris cloud before it interacts with something is genuinely difficult. A third possibility is simply that this is a statistical fluctuation, that the debris environment has natural variability that our monitoring programs, with their limited baselines of a few decades, have not yet characterized, and this is just the high end of normal variation. That would be the least alarming explanation. It may be the correct one, but it is not the certain one. And the Artemis II crew is currently travelling through whatever the true explanation is. They are not reading about this in a briefing document. They are inside it. They watched it happen, and they are now 90 minutes of flight time closer to home than they were when those flashes appeared, committed to a trajectory that will take them through it regardless of what the ultimate explanation turns out to be. The debris environment is one thread in a larger tapestry that makes this 72-hour window unlike anything in the history of human spaceflight. Each threat on its own would be manageable, or at least familiar in principle. Together, layered, simultaneous, all peaking in the same narrow window, they form something that has no direct historical precedent. And at the centre of all of it is a star that has been behaving throughout this mission as if it is trying to make a point. Part 3. The Turn Toward Earth. The turn toward Earth began at the lunar flyby, and from that moment forward, the mission clock became a radiation clock. Every hour the crew spends in transit is an hour of exposure to the full, unshielded, unfiltered radiation environment of deep space, because that is exactly where they are. Not near deep space, not on the edge of deep space, in it. And if you want to understand why this particular mission, in this particular moment, faces a radiation environment that is categorically more dangerous than anything the Apollo crews encountered, you need to understand what that environment is actually made of, because it is not one thing. It is a collection of simultaneous threats, each operating on a different timescale, each attacking the crew and the spacecraft in a different way, each with its own probability of crossing from manageable to catastrophic. Start with galactic cosmic rays, because they are the baseline, the floor, the background hum against which everything else is measured. Galactic cosmic rays, GCRs, are high-energy particles, primarily protons and heavier atomic nuclei, that do not come from our Sun. They come from out there, supernova remnants, neutron stars, energetic events in galaxies so distant that the light from them left before Earth existed. These particles have been accelerating through interstellar space for millions of years, and they arrive at our solar system from essentially every direction, at essentially all times, carrying energies so extreme that no practical spacecraft shielding can stop them. None. The material science to block a high-energy galactic cosmic ray does not exist in any operational spacecraft flying today, including Orion. These particles punch through the hull, interact with the structure, the equipment, the water stores, the food, and the bodies of the crew, and deposit ionizing radiation as they go, continuously, for the entire transit. Here is the thing about GCRs though, they are, in the grim accounting of deep space radiation, the manageable threat. Their flux is predictable, their biological effects are reasonably well characterized, the mission duration is short enough that the cumulative GCR dose, while significant and worth monitoring, falls within the established career radiation limits for astronauts. Flight surgeons know what the GCR numbers will look like when the crew lands. GCRs are the background noise of interplanetary space, uncomfortable background noise that would be headline news in any other context, but background noise nonetheless. What is not background noise, what is the thing that actually keeps the flight surgeons awake during this mission, is solar energetic particles. And to understand why SEPs are so much more dangerous right now than they were during Apollo, you need to understand where we are in the solar cycle. The Sun operates on an approximately 11-year cycle of magnetic activity. At solar minimum, the Sun is relatively quiet. Fewer sunspots, fewer flares, fewer coronal mass ejections. At solar maximum, the magnetic field is complex and unstable, active regions multiply across the solar disk, and significant flare and ejection events become far more frequent. We are currently near the maximum of solar cycle 25, and here is the detail that matters enormously and has not received nearly enough public attention. Solar cycle 25 has been stronger than the models predicted. The official forecasts issued before and during the rise of this cycle suggested a moderate maximum, comparable to or slightly below the relatively weak solar cycle 24 that preceded it. That forecast was wrong. Solar cycle 25 has exceeded expectations at essentially every milestone. More sunspots than predicted, more flares than predicted, more intense activity than the models said to expect. Why does that matter beyond the immediate mission? Because the same models that underestimated the cycle's intensity are the models that inform real-time space weather forecasting. The same models that told forecasters this cycle would be moderate are the models that assess the probability of significant events during the Artemis II return window. If the models were systematically off on the cycle prediction, they may be systematically off on the event probability estimates, not necessarily. Model performance on long-range cycle prediction and model performance on short-range event forecasting are different things. But the track record of the cycle forecast is worth keeping in mind when you are evaluating the confidence level on the daily flare probability assessments. For comparison, the Apollo missions flew during solar cycle 20, and the timing of those flights was, in retrospect, extraordinarily fortunate. Solar activity during the Apollo era was moderate by historical standards, and the specific windows of the Apollo lunar missions avoided major space weather events with a consistency that, when you examine it, looks less like careful planning and more like exceptional luck. The crews of Apollo received interplanetary radiation doses that were low by the standards of deep space exposure. The environment was benign. Nobody at the time fully appreciated how benign it was, because we had nothing to compare it to. We have something to compare it to now. The April 2026 environment is not benign. It is near maximum activity from a cycle running above its predicted level, and the Artemis II crew is flying home through it, with no ability to speed up and no ability to take shelter anywhere except the modest protection of the capsule itself. On April 3rd, 3 days before the lunar flyby, Earth experienced a G3 geomagnetic storm, the third level on a 5-point severity scale. A G3 event produces aurora visible down to mid-latitudes, disrupts satellite operations in ways that require active intervention, and can stress power grid infrastructure enough to require protective switching. It was driven by a coronal mass ejection that struck Earth's magnetosphere with enough force to shake it. The Artemis II crew, still in transit around the Moon, received elevated particle exposure from the energetic particle event associated with that storm. Then, the very next day, April 4th, Region 4409 fired the M7.5 flare. A G3 storm followed immediately by a near X-class flare in consecutive days, while 4 people are sitting outside the magnetosphere with no way to come home faster. The Sun was not warming up. It was showing the crew exactly what kind of environment they were committed to returning through. Now here is the radiation threat that receives the least attention, and may be the most operationally consequential of all of them, not because it's the most immediately dangerous to the crew's health, but because of what it has been doing to the hardware for the past 18 days. Since March 20th, 2026, electron flux in the near-Earth radiation environment has been continuously elevated above 1,000 particle flux units. 1,000 particle flux units is the threshold at which spacecraft operators in geostationary orbit, inside the partial shelter of Earth's magnetosphere, typically begin taking protective measures for sensitive electronics. The peak value measured during this 18-day stretch was 6,075 particle flux units, 6 times the action threshold for a spacecraft operating outside the magnetosphere without even the partial shelter that geostationary satellites benefit from for 18 consecutive days. The mechanism by which this harms a spacecraft is called deep dielectric charging, and it is one of those slow, invisible, accumulating threats that is easy to dismiss until you understand the endpoint. Energetic electrons penetrate the outer layers of spacecraft materials and embed themselves in the interior of insulating components, circuit boards, cable insulation, connector bodies, structural composites. They do not move freely through these materials. They accumulate, building internal charge distributions that create electric fields inside the bulk of the material itself, invisible to any external sensor, growing steadily as more electrons arrive and fewer find discharge pathways. After hours, this is a minor concern. After days, it is a meaningful engineering consideration. After 18 days continuously above threshold, in a spacecraft whose nominal design case did not assume this duration of elevated flux, it is a system that has been stressed in ways that are difficult to fully characterize from the outside. When accumulated charge reaches a sufficient level, it discharges, sometimes gradually and harmlessly, sometimes in a sudden internal electrical event that interacts with nearby circuits and produces what engineers call a single event upset, a bit flip in a logic register, a corrupted sensor reading, an unexpected software state, a command that was never issued appearing in a system log as though it was, navigation data, thruster control states, reentry sequencing software, environmental control systems. All of these run on digital electronics that have now been accumulating charge stress for 18 days in an environment above their nominal design exposure, and the return transit through the Van Allen belts, the final leg of the journey, the last radiation environment the capsule must cross before splashdown, will be the most concentrated single dose of the entire mission. The outer Van Allen belt, dominated by electrons, has been energized by the same elevated flux environment that has been stressing Orion's electronics for 3 weeks. The capsule that passed through it outbound 18 days ago passes through it again inbound in a configuration that is measurably more radiation stressed than it was at departure. Orion's Hera monitoring system tracks all of this in real time. The crew knows their numbers, mission control knows their numbers. What Hera cannot do is prevent the next bit flip, or predict which system will manifest the next anomaly, or tell anyone that a navigation calculation just ran on corrupted input. It is a dashboard, not a shield, and the dashboard has been reading elevated numbers for 18 days. The crew has no choice but to fly through it. They made that commitment when they left Earth. The radiation does not negotiate, does not pause, and does not care that the mission is historic. The question is not whether the environment is active. The question is what it decides to do in the next 72 hours, and whether the margins built into this spacecraft were designed for the environment that actually exists out there, or the one the model said would be there. Those are very different things, and right now, only one of them is real. Part 4, The Invisible War. On April 4th, 2026, a region of the Sun called Active Region 4409 released a flare. It was classified M7.5, just below the threshold for X-class, which is the highest category in the solar flare classification system. And I want to spend a moment on that classification because the way it gets reported in headlines can create a false impression of what actually happened. The flare classification system works on a logarithmic scale. Each letter category represents a 10-fold increase in X-ray flux over the previous one. A B-class flare is 10 times more energetic than an A-class. A C-class is 10 times more energetic than a B-class. An M-class flare is 10 times more energetic than a C-class flare. An X-class flare is 10 times more energetic than an M-class. The M7.5 event was not a minor incident that happened to fall close to a threshold, the way a 98-degree fever is close to 100. It was a significant, energetic, dangerous event that happened to fall just below an arbitrary categorical boundary in a classification system designed for broad administrative sorting, not for communicating precise risk to the public. When you read just below X-class, Translate that in your mind to the most energetic category of solar event, minus a rounding error. That is a more accurate picture of what fired at the crew on April 4th. But here is the thing, the classification almost doesn't matter. Because the real danger from this event has nothing to do with where it sits on a scale. The real danger is in the mechanism. And the mechanism of the April 4th flare is where this story gets genuinely frightening in a way that most coverage of this event has completely failed to communicate. Most dangerous solar events that have entered public awareness involve coronal mass ejections. CMEs are the things that dominate space weather headlines, massive magnetized clouds of plasma hurled into interplanetary space by solar eruptions, capable of stripping planetary atmospheres over geological time, capable of disrupting global electrical infrastructure, responsible for the Carrington event of 1859 that set telegraph offices on fire across North America and Europe. CMEs are real, serious, civilization-scale threats at the extreme end of their range. But they have one feature that makes them survivable with adequate preparation. They take time to arrive. A CME directed at Earth travels at somewhere between a few hundred and a few thousand kilometers per second, depending on the energy of the eruption. Even the fastest CMEs take several hours to reach Earth. The average is closer to 1 to 3 days. That is a warning window. That is the interval during which space weather forecasters can issue alerts, spacecraft operators can power down vulnerable systems, astronauts can move to shielded shelter positions, and grid operators can take protective measures. CME-based radiation threats are serious, but they move at speeds that permit human response. The threat announces itself before it arrives. The April 4th event did not announce itself. It could not. Because it was not a CME region 4409 produced what solar physicists call a confined eruption. The magnetic field structure of the region, the complex twisted topology of field lines that had been building for days as the region developed, did not open to space during the eruption. The field lines that normally reconnect and release a CME stayed closed, contained. The energy of the eruption had nowhere to go except into accelerating particles directly, right now, into the surrounding space. Solar energetic particles, SEPs, are atomic nuclei, primarily protons but also helium nuclei and heavier elements that get accelerated by the flare event itself to velocities that are a substantial fraction of the speed of light, not the speed of a CME, a fraction of the speed of light, and alongside those particles the electromagnetic radiation from the flare, hard X-rays and gamma rays, travels at the actual speed of light, no fraction required. The distance from the Sun to the Orion capsule during this phase of the mission is approximately 1 astronomical unit, 150 million kilometers, the same as the Earth-Sun distance. Light covers that distance in 8 minutes and 20 seconds, which means the first indication the crew had that an M7.5 flare had just occurred on the Sun was the radiation from it physically arriving at their position 8 minutes and 20 seconds after ignition. Not a warning, not a forecast, not a notification from mission control who had been watching the region. The event itself, arriving as the announcement of its own existence. The warning and the threat are the same thing, separated by the time it takes light to travel from the Sun to where you're sitting. Now hold that thought and think about the Orion shelter protocol. If the crew needs to move to the most protected area of the capsule, which involves physically repositioning themselves, repositioning equipment to increase the mass shielding around the shelter zone, configuring the habitat for maximum radiation protection, the full deployment of that protocol takes approximately 1 hour from initiation to completion. 1 hour against an 8-minute light travel time. Against a 0-minute warning window, really, because as I just explained, the warning and the arrival are the same physical event. There is no gap between notification and exposure during which you can execute an hour-long shelter procedure. By the time you finish step 1, the peak radiation flux of an impulsive flare has already passed through you. I want to be precise here because this is not a criticism of mission planning, and it is not evidence that someone made an error. This is a fundamental physical constraint that no engineering decision can overcome. You cannot shelter faster than the threat travels. The Orion shelter protocol exists and is a real and meaningful protective measure, but it was designed for CME-associated radiation events, where hours of warning allow orderly preparation. For an impulsive confined eruption like the April 4th flare, the shelter protocol is not a protective response to the threat. It is a post-exposure damage limitation measure. The crew does not shelter to avoid the radiation. The crew shelters to reduce continued accumulation after the initial dose. The one that arrived in the first 8 minutes has already been delivered. That is a very different thing from what most people imagine when they hear the words radiation shelter protocol. The biological consequences of that initial dose depend on several factors that interact in complex ways. The energy spectrum of the particles, how fast they were moving when they hit, determines how deeply they penetrate biological tissue and how much ionizing damage they do along their path. The shielding geometry of wherever the crew member happened to be positioned in the capsule at the moment of arrival determines how much material the particles had to pass through before reaching them. A crew member floating near the centre of the capsule has more shielding mass around them than one positioned near a window or a hatch. And the total fluence of the event, the integrated particle flux over time, determines the cumulative dose delivered before the shelter is fully deployed and reducing further exposure. Inside a spacecraft, the situation is complicated further by secondary radiation. When high-energy particles interact with the hull, the equipment, the water stores, and everything else the capsule is made of, those interactions produce additional radiation, neutrons, scattered gamma rays, lower-energy secondary particles moving in directions that the original primary particles were not moving. The radiation environment inside the capsule during an SEP event is not simply a reduced or attenuated version of the external environment. It is a qualitatively different environment, created by the interaction of the external flux with the spacecraft itself, producing a secondary field that fills the interior from all directions simultaneously. This is why more shielding is not always straightforwardly better. At certain energies, a thicker shield produces more secondary radiation than a thinner one, and you can end up worse off than if you had less material around you. The optimization of spacecraft radiation shielding is genuinely complex, and the specific performance of Orion's shielding geometry under the exact particle energy spectrum of the April 4th flare is not a number that exists in any published document, because it depends on variables that can only be fully characterized after the fact. The relative biological effectiveness framework accounts for the fact that different types of radiation cause different amounts of cellular and DNA damage for the same amount of deposited energy. A dose of 1 gray from high-energy protons does more biological damage than a dose of 1 gray from X-rays, because the protons create a denser track of ionization along their path through tissue, causing clustered DNA damage that the cell's repair mechanisms struggle to address. The RBE for the protons that dominate SEP events is higher than for the electromagnetic radiation that dominates most radiation environments people are familiar with on Earth. This means the effective biological dose from an SEP event, the dose measured in units that account for biological impact rather than just physical energy deposition, is higher than a naive reading of the physical dosimetry would suggest. The crew's radiation exposure monitors measure physical dose. The biological consequence is calculated from that measurement using RBE factors that carry their own uncertainties. Now step back and look at the probability picture for the return window as a whole, because the April 4th flare was one event in a dynamic environment that was not static during the transit. The Space Weather Prediction Center was tracking approximately 10% per day probability of an R3 or higher radio blackout event, which corresponds to an X1 or larger flare, and approximately 10% per day probability of an S1 or higher solar radiation storm. These are independent daily assessments. If you treat the days as roughly independent, a simplification, but a reasonable approximation for a back-of-envelope calculation, the cumulative probability of at least one significant event occurring during the 72-hour return window works out to somewhere between 25 and 30%. 1 in 4 odds, roughly. Better than 1 in 3 odds that something meaningful happens during the specific window, when the crew is most exposed, most committed to their trajectory, and least able to take any protective action beyond what the capsule itself provides. And the threat environment was not fixed around a single decaying source. Region 4409, the region that produced the April 4th flare, was indeed declining in magnetic complexity after its eruption. Active regions typically evolve after a major event as the magnetic topology reconfigures, but active regions do not always decline monotonically, and region 4409 was not the only player on the solar disk. Region 4412 was rotating into a position that placed it in direct line with the Orion capsule's location during the return transit. a new active region, freshly emerged from the solar interior, where its magnetic history was unknown, moving into an orientation where any eruption it produced would be directed toward the crew. The Sun was not presenting a single, diminishing threat. It was presenting a dynamic, shifting threat environment with multiple simultaneous active sources and a transit window long enough to give all of them time to act. Let me tell you about the threat that has received the least public attention throughout this entire mission, because I think it may ultimately prove to be the most consequential for the hardware, and therefore for the crew's ability to survive the final phase of the return. Since March 20th, 2026, 18 days before the start of the April 7th return window, electron flux in the near-Earth radiation environment has been continuously elevated above 1,000 particle flux units. To give that number context, 1,000 particle flux units is the threshold above which operators of geostationary satellites, spacecraft sitting 36,000 kilometers above Earth's surface, inside the partial shelter of the magnetosphere, typically begin implementing protective measures for sensitive electronics. The Orion capsule has spent its entire mission outside the magnetosphere, with no partial shelter, no threshold-triggered protection procedures, operating in the full ambient radiation environment. And the peak flux during this 18-day stretch reached 6,075 particle flux units, 6 times the level that triggers protective action for spacecraft that have the benefit of being inside the magnetosphere. The process by which this harms a spacecraft is called deep dielectric charging. Energetic electrons, particles moving at a significant fraction of the speed of light, penetrate the outer surface layers of spacecraft components and become trapped in the bulk of insulating materials, circuit boards, cable insulation, composite structural panels, connector housings. These materials do not conduct electricity freely. The electrons cannot move through them to find discharge pathways. They accumulate. They pile up in the interior of the material, building internal electric field distributions that are invisible to any external measurement, that grow steadily as long as the flux remains elevated, and that the spacecraft's grounding systems designed to handle surface charging, not internal bulk charging, cannot adequately dissipate. After a few hours of elevated flux, the accumulated charge is small and the risk is low. After a few days, it is a meaningful engineering concern. After 18 consecutive days above the threshold that triggers protective action in geostationary orbit, it is a system that has been operating outside its nominal design envelope for a duration that would prompt a formal anomaly investigation in any satellite operations program. When the accumulated internal charge reaches a critical level, it releases. The discharge can be gradual and dissipate harmlessly, or it can be sudden, a rapid internal electrical event that propagates through adjacent circuit elements and produces what engineers call a single event upset, a bit flip. A memory register that was holding a 0 now holds a 1. An instruction in the flight software that was supposed to execute in a particular way gets corrupted and executes differently or not at all. A sensor that has been accurately reporting a temperature or a pressure or a valve position suddenly reports a different value, a value that is wrong, but that the system has no way to flag as wrong because it falls within a plausible range. Navigation solutions built on corrupted sensor inputs. Thruster commands derived from navigation solutions built on corrupted sensor inputs. Reentry sequencing logic running on flight software with a corrupted instruction. These are not hypothetical failure modes invented for dramatic effect. They are documented real-world failure mechanisms that have caused anomalies and losses in operational satellite programs. The difference between those programs and Orion is that those satellites did not have people in them whose survival depended on the electronics working correctly at Mach 32. Modern spacecraft electronics incorporate error correction codes, mathematical redundancy built into memory storage that allows single-bit errors to be detected and corrected automatically before they propagate. This is real protection, and it is not trivial. But error correction has architectural limits. It is designed to handle isolated, infrequent bit errors. It handles simultaneous multiple-bit errors less reliably. It cannot correct errors in the error correction logic itself if that logic has been corrupted. And it cannot catch errors that produce outputs that are wrong but numerically plausible, values that pass through every check because they look like valid data. The HERA system, the high-energy radiation monitor architecture aboard Orion, provides real-time monitoring of the radiation environment and cumulative dose tracking for both the crew and the spacecraft systems. Mission Control has access to this data continuously. The crew knows their numbers. The flight surgeons know the hardware exposure history. None of that changes what the hardware has experienced over 18 days. HERA is a measurement system. It tells you what has happened and what is currently happening. It does not undo what has already been deposited in the dielectric materials of the spacecraft's electronics. It does not prevent the next discharge. It does not predict which circuit will experience the next upset, or when or what the consequences of that upset will be in the context of whatever the spacecraft is doing at the moment it occurs. The crew is heading home through all of this because the return window is fixed and the physics owns the schedule. They cannot leave early. They cannot take a faster route. The radiation does not pause while they transit. The electron flux does not care that the mission is historic. The sun does not know that 4 people are depending on it to remain quiet for 72 more hours. The 72-hour question is not simply about whether the crew absorbs a radiation dose that exceeds their biological limits. It is about whether the systems they depend on, the navigation computers, the thruster controllers, the reentry sequencing software, the environmental monitors, continue to function correctly through the final phase of a mission, during which they have been accumulating radiation stress for 18 consecutive days at levels above the threshold that would trigger formal protective action in any other operational spacecraft program. The radiation is not the ending. The radiation is the environment in which the ending happens, and the ending is coming at Mach 32, through 5,000 degrees of plasma, on a heat shield that has never been tested like this before. But that is the next part of the story. Part 5. The probability stack. There is a concept in risk analysis that does not have a widely known name outside of engineering and actuarial communities, but which describes exactly what the Artemis II crew is facing right now with a precision that should make anyone paying attention genuinely uncomfortable. It is sometimes called compound risk, or risk stacking, and once you understand it, you will never look at a mission like this the same way again. Because the way most people think about risk in spaceflight, and honestly, the way most public communications about spaceflight risk are structured, is fundamentally incomplete. It accounts for the individual pieces. It misses what happens when the pieces are all active at the same time. Here is how risk analysis normally works in aerospace engineering, and why it works well for the problems it was designed to solve. You identify a failure mode, a specific thing that could go wrong. The heat shield performs below specification. A solar flare arrives during a period of peak crew exposure. A micrometeoroid strikes a critical system component. You assign that failure mode a probability, derived from testing, from modelling, from historical data on similar systems in similar environments. You assign it a severity. How bad is the outcome if this specific thing happens? And then you make engineering decisions to reduce either the probability or the severity or both. You add redundancy so that a single failure does not cascade. You add shielding so that the exposure is reduced. You change the trajectory to avoid the highest risk environment, and for any single threat analysed in isolation, this approach works. It works well. The progressive improvement in the safety record of human spaceflight over 6 decades is directly attributable to the rigorous systematic application of exactly this kind of failure mode analysis to every component, every system, every foreseeable scenario. The problem, and this is the problem that Artemis II is currently navigating in real time, is what happens when multiple independent threats, each of which has been individually managed to an acceptable probability level, are all simultaneously active within the same exposure window. Because the mathematics of that situation is deeply counterintuitive, and the intuitive version that most people carry around in their heads is wrong in a way that significantly underestimates the actual risk. Let me give you the number directly. If you have 5 independent threats, and each of them has a 10% probability of causing a problem, your intuition probably says the overall risk is somewhere around 10%, maybe a bit higher because there are 5 of them, so perhaps you think 50%. Both of those intuitions are wrong. The actual probability that at least one of those 5 threats causes a problem is roughly 41%, not 10%, not 50%, 41%, nearly 1 in 2.5. And that is the calculation for perfectly independent threats. Threats that do not interact with each other, do not amplify each other, do not create conditions that make each other more likely or more severe. In the real environment the Artemis II crew is transiting right now, that independence assumption does not hold. The threats are not independent. They interact. they compound each other in ways that push the actual risk profile further from the idealized calculation and closer to something that is genuinely difficult to model with confidence. Think about how the interactions work in practice. A solar flare event produces a surge of energetic particles that can cause single event upsets in spacecraft electronics. If that surge occurs at a moment when the crew needs to execute a time-critical maneuver, a navigation correction, a systems reconfiguration, a response to another anomaly, a corrupted sensor reading, or a flight software upset during that window is a different event than the same upset occurring during a quiet period when the crew has time to diagnose and respond. A micrometeoroid strike on a sensor system that is already operating in a degraded state from 18 days of electron flux charging produces a different outcome than the same strike on a fully nominal sensor. The degraded system has less margin to absorb the impact of an additional stress event. It is already closer to its failure threshold. The strike that would be survivable under nominal conditions may not be survivable under conditions that have been grinding at the system's margins for 3 weeks. And then there is the human element, which engineering risk analysis has historically struggled to incorporate with full honesty. The crew of Artemis II has been monitoring a dynamic, multi-threaded threat environment for days. They have been tracking radiation levels, watching solar activity forecasts, processing information about the debris environment they observed from the lunar far side, managing the psychological reality of being committed to a trajectory they cannot shorten through a situation that keeps producing new information. That sustained cognitive and psychological load affects decision-making. It affects the speed and accuracy of response to new events. It affects the quality of judgment under time pressure. These are not character flaws in the crew. They are documented, well-studied features of human performance under prolonged stress. And in the probability stack that Artemis II is navigating, human performance under stress is one of the variables. Apollo 13 is the reference point that everyone reaches for when discussing compound risk in human spaceflight, and it is worth examining carefully, not just for the similarities to Artemis II's situation, but for the differences, because the differences are where the real insight lives. The Apollo 13 accident began with a single mechanical failure. The rupture of oxygen tank 2 in the service module, a failure that traced back through a cascade of manufacturing decisions, ground handling procedures, and design choices that had been accumulating for years before the mission launched. The rupture was not predicted. It was not in the failure mode analysis as a credible near-term risk. It happened anyway, because complex systems that have been stressed in ways that are not fully documented sometimes fail in ways that the models did not anticipate. The rupture cascaded through the spacecraft's systems in ways that consumed consumables, eliminated redundancy, and left the crew with a survival problem that had no pre-planned solution. They were in a situation that the mission designers had not specifically modelled, with resources that were not intended for the purpose they now had to serve, at a distance from Earth that allowed no external intervention. They survived because Jim Lovell, Jack Swigert and Fred Hayes performed at an extraordinary level, because the flight controllers at Mission Control performed at an extraordinary level, because the specific sequence of the failure and the specific configuration of the available resources happened to permit a solution that could be improvised in the time available. People called it a miracle. Engineers called it a recoverable system failure. Both descriptions are accurate, and neither one fully captures what it actually was, which is a situation where the margin between catastrophe and survival was thinner than anyone involved would have been comfortable with if they had seen the full picture in advance. Now here is the critical distinction between Apollo 13 and what Artemis II is facing. Apollo 13 had a problem, a specific, identifiable, diagnosable problem. The oxygen tank ruptured. Once that happened, the failure mode was known. The resources were inventoried. The constraints were defined. The crew and mission control could work the problem, could apply intelligence and creativity and extraordinary effort to a situation that, however dire, had a definable structure. There was a thing that had gone wrong, and the task was to find a way to get home despite that thing. Artemis II does not have a problem in that sense. The vehicle is performing nominally. No alarm is sounding. No system has failed. What Artemis II has is an environment, a radiation environment running above its predicted level, a debris environment producing observations that do not fit the baseline model, an electron flux exposure extending across 18 days at levels that exceed the threshold for protective action in other operational spacecraft programs. a heat shield about to execute a re-entry profile that was redesigned after the first flight revealed unexpected behaviour on a trajectory that has never been validated with this specific design. None of these is a failure. Each of them is a condition, a way in which the system is operating closer to its margin than the nominal design case assumed it would be. And here is why that distinction matters so profoundly for the crew's situation right now. You can work a problem, you cannot work a probability distribution. When Apollo 13's oxygen tank ruptured, the crew had a specific task: survive this specific failure using these specific available resources. The task was defined by the failure. Here, the crew's task is to keep all systems functioning correctly through 72 hours of an environment that may or may not produce an event that crosses a threshold that may or may not be where the pre-mission analysis said it was. They cannot solve the radiation. They cannot fix the debris environment. They cannot modify the electron flux. They cannot change the re-entry profile or add validation data to the heat shield's test history. They can monitor. They can respond to anomalies as they emerge. They can execute the procedures they have trained for. But the outcome does not depend primarily on what they do. It depends on what the environment does, on whether the probability distributions that describe each threat resolve favourably across all of them simultaneously during the specific 72-hour window in which the crew is exposed. That is a profoundly different psychological and operational reality than Apollo 13. The Apollo 13 crew had agency. Their actions directly influenced the outcome. The Artemis II crew has procedures and monitoring and the training to respond to events, but in a compound risk environment where the threats are environmental rather than mechanical, where the margins are statistical rather than physical, where the failure mode is not a rupture or a fire but a probability that accumulates across multiple dimensions simultaneously, the crew's agency is constrained in ways that have no real parallel in previous human spaceflight experience. What the compound risk framework tells us, what the mathematics insists on, regardless of how uncomfortable the conclusion is that a mission can be well designed, carefully planned, and staffed by exceptional people and still face an overall risk profile that is significantly higher than any individual component of the risk assessment suggests. 5 threats each managed to 10% do not produce a 10% mission. They produce a 41% mission, at minimum, before you account for the interactions and dependencies that push the real number higher still. The individual engineering decisions that produced each of those 10% numbers may all be correct and defensible. The aggregate outcome of making all of them simultaneously is a different calculation than any of them individually. The crew knows this. Mission control knows this. The flight directors and the flight surgeons and the trajectory analysts tracking every data point from the Orion capsule as it closes the distance to Earth, they all know that what they are managing right now is not a single threat with a single mitigation. It is a probability stack in a dynamic environment, with a fixed window and a fixed trajectory and 4 people at the end of it who need everything to keep working for 72 more hours. The crew's job is not to solve anything. Nothing needs to be solved. Everything is working. The job is to keep everything working through the radiation, through the electron flux, through whatever the sun decides to do next, through the debris environment they watched demonstrating its activity from 4,000 miles beyond the moon until the Earth's atmosphere takes over, until the capsule hits the entry interface and the physics of re-entry become the dominant reality and the probability distributions of deep space stop mattering. That moment is coming, the atmosphere is waiting, and between here and there the probability stack is still running. Part 6. The physical threats. Before we arrive at the re-entry, the final gate, the point at which everything either holds together or it doesn't, there are 2 more threads in this picture that need to be pulled, because they complete the environmental portrait of what the Artemis II crew is actually flying through. Not the environment that was modelled before the mission launched. The environment that exists right now, in real time, as the capsule closes the distance to Earth. On April 8th, 2026, while the crew is midway through their 72-hour return transit, an asteroid designated 2026 GD will make its closest approach to Earth. The object is estimated at 10 to 25 meters in diameter, roughly the size of a large house at the small end, a modest office building at the large end. It is travelling at 12.66 kilometers per second, which works out to 45,576 kilometers per hour. Its closest approach distance will be approximately 0.65 lunar distances, roughly 250,000 kilometers from Earth. And I want to be direct and precise about what this means before anyone draws the wrong conclusion. 2026 GD will not hit Earth. Its trajectory does not intersect with the Orion capsule. There is no collision scenario here. This is not a hidden danger I'm about to dramatically reveal, but context matters more than the headline number. The average distance from the Earth to the Moon is 384,000 kilometers. 2026 GD will pass at 250,000 kilometers. That is inside the Moon's orbital distance. Below it, a rock the size of a building travelling at over 45,000 kilometers per hour will pass between the Earth and the Moon in the same volume of near-Earth space that the Artemis II crew is currently transiting, while those 4 human beings are the only people in history to have ever been in that volume aboard a crewed spacecraft. The asteroid is not the threat. I want to be clear about that, but it is something more interesting than a non-event. It is a precisely timed, vividly concrete reminder that the space the crew is moving through is not the featureless empty void that the word space tends to conjure. It is a dynamic system, a busy one. Objects move through it continuously, at velocities that make any collision a physics problem rather than a survivability question. And the ones we have named and catalogued are not all of the ones that are there. This is the part of the asteroid story that deserves more attention than it typically receives. The catalogue of near-Earth asteroids maintained by NASA's Center for Near-Earth Object Studies and ESA's Planetary Defense Office is genuinely impressive. It represents decades of systematic survey work and is comprehensive for objects above roughly 140 meters in diameter. 140 meters is the threshold above which an impactor would cause regional scale damage on Earth, the kind of event that would affect an entire metropolitan area or a significant fraction of a small country. For objects above that size, our catalogue coverage is good. For objects below that size, it degrades rapidly. Objects in the 10 to 25 meter range, the range that includes 2026 GD, are detectable with current technology, but the catalogue is not comprehensive. We find the ones we happen to look for in the survey windows that happen to be available, with the telescope resources that happen to be pointed in the right direction. The ones we have found are not all of the ones that exist. They are not even close to all of the ones that exist. The Chelyabinsk impactor of 2013, the event that injured over 1,000 people in Russia and shattered windows across a city, was approximately 18 to 20 meters in diameter. It was completely unknown before it entered the atmosphere. Nobody saw it coming. It was inside the uncharted population. The crew of Artemis II is travelling through a volume of space that contains an unknown number of objects in exactly that size range. Objects large enough to be catastrophic if they struck the capsule, small enough to be invisible in any catalogue, moving at velocities that make the question of impact purely probabilistic rather than something that could be avoided even with warning. 2026 GD is not the threat. It is the visible member of an invisible population, the one object in that range that we happen to have found and tracked, wearing a name tag in a crowd where most of the crowd is anonymous. The crew's micrometeoroid shielding is not designed for objects in this size range. No practical spacecraft shielding is, or could be. The probability of an encounter with a damaging object in this population is low, genuinely low, not dismissively low, but it is not zero, and it is higher when the debris environment, as we have already established, appears to be running above the baseline predictions. Now let's go back to the lunar impacts with a more analytical eye, because the physics of what the crew watched deserves a more careful examination than the initial description of explosions on the Moon fully conveys, and that physics connects directly to the question of what the Orion capsule is flying through on its way home. Hypervelocity is not simply a faster version of fast. It is a qualitatively different physical regime with its own mechanics, its own failure modes, and its own engineering challenges that do not exist at lower velocities. Below roughly 3 kilometers per second, when two solid objects collide, the dominant physics is mechanical. Materials deform, compress, crack, and fracture. The energy is absorbed through structural deformation. At 3 kilometers per second and above, something fundamentally different happens. The kinetic energy of the collision exceeds the binding energy of the materials involved, Both the projectile and the target material at the impact point vaporize instantaneously. Not melt, vaporize. The collision produces a plasma flash, a brief point of matter at temperatures comparable to the surface of the Sun, and the resulting crater is not carved by the physical passage of the projectile through the target. It is excavated by the explosive expansion of the plasma outward in all directions from the impact point. This is why hypervelocity impact craters on the Moon are circular regardless of the angle at which the impactor arrived. An oblique impact at hypervelocity produces the same symmetric plasma explosion as a vertical one, because the geometry of the explosion does not depend on the geometry of the approach. What the Artemis II crew watched on the lunar surface was not rocks hitting rocks. It was instantaneous conversions of kinetic energy into plasma events, miniature versions of the same physics that created every crater on the Moon over 4.5 billion years, happening live, in real time, close enough to watch. The engineering response to hypervelocity impacts in spacecraft design is the Whipple shield, first proposed by astronomer Fred Whipple in 1947 and implemented in various forms on essentially every crewed spacecraft since. The concept is elegant in its exploitation of the very physics that makes hypervelocity so destructive. A Whipple shield places a thin outer layer, called a bumper, at a standoff distance from the main pressure hull of the spacecraft. When a small high-velocity particle strikes the bumper, the particle and a small amount of bumper material vaporize on contact, producing exactly the plasma expansion that makes hypervelocity impacts so energetic. But now that plasma expansion is happening in the gap between the bumper and the hull, not at the hull itself. By the time the expanding debris cloud reaches the main hull, it has spread its energy across an area many times larger than the original particle's cross-section. The distributed impact that arrives at the hull is survivable. The concentrated impact that would have arrived without the bumper would have punched straight through. Whipple turned the physics of hypervelocity destruction into a protection mechanism. That is genuinely brilliant engineering. But Whipple shield protection has explicit non-negotiable limits that the design documentation states clearly and that are worth understanding precisely. The shield provides probabilistic protection against particles up to a certain size threshold. Below that threshold, the vaporization and expansion work as designed, and the hull survives at acceptable probability. Above that threshold, the incoming particle carries enough mass and energy that the debris cloud it produces after vaporizing the bumper still has sufficient concentrated energy to penetrate the hull. And significantly above that threshold, in the size range of the objects that produce the flashes the Artemis II crew watched, the Whipple shield is not a meaningful barrier in any engineering sense. If an object capable of producing a kiloton-scale impact on the lunar surface struck the Orion capsule, the outcome would not be a penetration that could be repaired or a system anomaly that could be managed. There would be nothing to analyze afterward. The capsule and its contents would become part of the debris environment. Those specific large objects are not, of course, the actual threat to the capsule. The probability of the capsule's trajectory intersecting with an object large enough to produce a kiloton-scale impact is genuinely negligible. But this is where the power law-size distribution of debris populations becomes operationally important, and where the elevated lunar impact rate that the crew observed starts to have direct implications for the micrometeoroid risk during the return transit. Debris populations in space, whether we're talking about natural meteoroids, asteroid family fragments, or cometary debris, follow what mathematicians call a power law-size distribution. This means that for every object of a given size, there are predictably many more objects of half that size, and even more objects of a quarter that size, and so on, in a ratio that remains roughly constant across a wide range of scales. The specific exponent of that power law varies by population, and has been measured for the near-Earth debris environment using a combination of lunar crater counting, satellite impact sensors, and ground-based detection programs. The practical consequence is this. If the rate of large objects, the kiloton-capable impactors that produce visible flashes on the Moon, is elevated above baseline predictions, then the power law demands a corresponding elevation at every smaller size in the distribution. More large objects per hour means more medium objects per hour means more small objects per hour, in a ratio that the power law constrains. The objects at the small end of that distribution, the grain of sand to marble-sized particles that form the continuous background of the micrometeoroid environment, are exactly the population that Orion's Whipple shield is designed to handle. The objects in the middle of the distribution, larger than the shield's design basis, smaller than the kiloton-capable impactors, are the population that represents the actual catastrophic risk to the capsule. And if the large object rate was elevated during the observation window, the power law implies that the middle population was elevated too. Not by a factor that changes a negligible probability into a likely one, but by a factor that shifts the probability above what the nominal shielding design assumed as its baseline. Whether it shifts it by enough to matter is a question that cannot be answered without knowing whether the elevated rate the crew observed was a genuine environmental increase or a detection artifact, a question that, as I have already established, does not currently have a confirmed answer. They are not flying through theory, they are flying through what they just watched, and what they just watched was active in a way that our models did not predict. One more variable belongs in this picture, and I have been saving it because its timing is so extraordinary that it demands careful handling. Present it too dramatically, and it sounds like conspiracy. Dismiss it too quickly, and you're ignoring a genuine modelling gap in the environment the crew is depending on models to navigate safely. Comet C/2026A1, designated maps, reached perihelion, its closest approach to the Sun, on April 4, 2026. The same day as the M7.5 flare from region 4409, its perihelion distance placed it within the solar corona itself, a sun grazer, an object travelling closer to the Sun than any planet, threading through the outer atmospheric layers of our star at speeds that exceed anything else in the solar system. Sun grazers occupy a special category in solar astronomy because they do not simply pass near the Sun, they interact with the solar environment in ways that objects at greater distances do not. The solar corona is not empty space with a star at the centre. It is a structured, magnetised plasma, threaded through with magnetic field lines that organise the flow of charged particles throughout the inner solar system, that control the topology of coronal active regions, that mediate the connection between surface activity and the interplanetary environment through which the crew is now travelling. A massive object moving through that structured plasma at high velocity does not pass through transparently. It drags through the field lines, it creates disturbances in the local magnetic topology, it deposits material, cometary dust, cometary ions, directly into the coronal plasma. The coronal environment downstream of the comet's path is not identical to the coronal environment upstream of it. Whether any of that matters for the April 4th flare is a question that has not been answered by any published analysis. The causal connection between the map's perihelion and the region 4409 eruption has not been established. I want to be clear about that, because the distinction between these two things happened on the same day, and these two things are causally connected, is exactly the kind of distinction that serious analysis requires. Correlation on a single data point is not evidence of causation. It is a coincidence that may or may not be meaningful, and the honest answer is that we currently lack the analytical tools to determine which. But here is what we can say with confidence. The Space Weather Prediction Centre's operational forecast models do not include sun-grazing comets as variables. They do not include the potential effect of a massive object transiting the solar corona on the magnetic topology of active regions, or on the frequency of confined eruptions, or on the energy spectrum of solar energetic particles accelerated by those eruptions. This is not a failure of the forecasting program. It is an honest reflection of the current state of solar physics. The interaction between sun-grazing comets and the coronal magnetic environment is not well enough characterized to be incorporated into operational models that need to produce reliable, actionable probability assessments in real time. The models do what they can do well. They do not do what they cannot yet do. The crew is depending on those models. The probability assessments for the return window, the 10% per day flare probabilities, the cumulative 25 to 30% radiation storm risk, the estimates of the ongoing particle environment are derived from models that do not include the MAPS comet as a variable. If the comet's perihelion passage altered the coronal environment in ways that increased the probability of flare activity or enhanced the energy of the particle environment, and we cannot confirm or rule out that it did, then the probability assessments may be systematically underestimating the actual activity level. Not because the forecasters made errors in applying their models, because their models do not contain everything that is happening in the system they are modelling. Every model is a simplification. Every simplification leaves something out. The question that matters for the crew of Artemis II is whether the things being left out are small enough to be irrelevant, or large enough to be the difference between the probability assessments being right and the probability assessments being wrong in a direction that matters? That question does not have a confirmed answer. It has an environment that is currently providing in real time, around 4 people who are committed to a trajectory they cannot change, heading toward a re-entry that has never been tested exactly like this, carrying 18 days of radiation stress in their electronics and the memory of kiloton-scale explosions on a lunar surface that should have been quieter than it was. The model said it would look one way out there. The crew can see what it actually looks like, and those are not quite the same picture. Part 7. The Final Gate. On November 16, 2021, the uncrewed Orion capsule from Artemis I splashed down in the Pacific Ocean after completing its 25-day loop around the Moon. The recovery teams pulled it out of the water, the engineers got their hands on it, and what they found when they examined the heat shield started a conversation inside NASA that has not fully resolved itself, and will not fully resolve itself until April 10th, 2026, when the answer gets written in fire and physics at Mach 32 over the Pacific. Some conversations in engineering end in meeting rooms with a corrective action plan and a revised specification document. This one ends in the ocean, with 4 people either in it or not. More than 100 distinct locations on the Avcoat. Ablative material had behaved differently than the computer simulations predicted. 127 to be precise. On a system where the margin for catastrophic failure is not a percentage point or a safety factor of 2, where the margin is binary, where the heat shield either protects the crew or it does not, and there is no partial credit, finding 127 locations where the material did not behave as predicted is not a minor variance report. It is a signal that the model and the physical reality are not the same thing. And before we get into what that means for Artemis II specifically, I want to spend some time on what Avcoat actually is and how it works, because the heat shield of the Orion capsule is one of the most philosophically strange pieces of engineering ever built for human spaceflight. And understanding that strangeness is essential to understanding why the Artemis I anomaly matters as much as it does, and why the decision that was made in response to it carries the weight it carries. Most protective systems in engineering work by being strong, or by being resistant, or by being redundant. Armor plates absorb impacts. Pressure vessels contain internal forces. Structural beams distribute loads. The underlying principle is that the protective element survives the threat and continues protecting. Avcoat does not work this way. Avcoat protects the capsule by being destroyed. Deliberately, precisely, in a carefully engineered sequence of destruction that carries thermal energy away from the vehicle in the vaporized products of its own consumption. The material chars. It cracks. It gasifies at a controlled rate as temperatures climb past 5,000 degrees Fahrenheit. And in that gasification, in the process of the material literally burning away from the capsule surface, the heat that would otherwise conduct inward toward the crew is carried outward and away in the ablation products. The heat shield sacrifices itself so that everything behind it survives. The design requirement is not that the Avcoat withstand re-entry. It is that the Avcoat fail in exactly the right way, at exactly the right rate, across exactly the right spatial distribution of the heat shield face, so that the thermal energy never reaches the structure it is protecting. This is why heat shield engineering is so extraordinarily difficult, and why deviations from the predicted ablation pattern are so much more concerning than they might initially appear. You're not designing something to be strong, you're designing something to fail correctly under conditions that no ground-based test facility can fully replicate, at temperatures that exist in very few places in the solar system, at velocities that produce physical regimes that ground testing can only approximate. The computer simulations that predict how Avcoat will behave during re-entry are built on physical models derived from a combination of arc jet testing, flight data from previous missions, and mathematical representations of ablation chemistry and heat transfer. Those simulations are the best tools available, and the Artemis I flight demonstrated that the best tools available predicted the wrong behavior in 127 locations on the first flight of the system. The mechanism identified through post-flight investigation was gas trapping. During the manufacturing process, a complex layered procedure that applies Avcoat in segments across the curved surface of the heat shield, small pockets of gas became embedded within the material. Not large voids, not structural defects visible to inspection, Small, distributed microscopic pockets of trapped gas that the manufacturing quality control process did not catch, because catching them requires the kind of detailed internal inspection that is not part of routine production verification for this material. Under the extreme temperatures of re-entry, those gas pockets expanded. The expanding gas disrupted the local ablation process in each affected location, causing the material to char in a pattern that deviated from the simulation's prediction. The structural integrity of the heat shield as a whole was not compromised. The Artemis I capsule survived re-entry. No crew would have been killed by what happened to that heat shield on that flight. But, and this is the sentence that needs to be read carefully, no crew would have been killed by what happened on that specific flight, under those specific re-entry conditions, at that specific vehicle mass and centre of gravity, with that specific thermal load distribution. The question of what would have happened to a crewed capsule, with the additional mass of 4 people and their equipment, on the direct re-entry profile that Artemis II will fly, is a question the Artemis I flight data cannot answer, because Artemis I did not fly that profile. NASA's response to the anomaly was to change the re-entry profile. The original Artemis II re-entry was designed as a skip trajectory. The capsule enters the upper atmosphere at a shallow angle, uses the aerodynamic lift generated by its shape to pull out of the initial descent, briefly exits the atmosphere, and then descends again on a steeper final approach. The skip maneuver is elegant in its engineering purpose. By distributing the re-entry energy across 2 atmospheric passes rather than 1, it reduces the peak heating rate that the heat shield must survive at any single moment. Lower peak heating rate means lower peak temperature means less thermal stress on the ablative material. The skip profile was specifically designed to be gentler on the heat shield than a direct plunge would be. And it was the skip profile that produced 127 anomalous ablation locations. The investigation identified the thermal sequence of the skip as a potential contributor to the gas-trapping failure mode. The specific pattern of temperature rise during first entry, followed by partial cooling during the atmospheric exit phase, followed by temperature rise again on final descent, may have created the conditions under which the trapped gas pockets expanded at rates that disrupted the ablation process. The proposed fix was straightforward in its logic. Eliminate the skip phase, remove the 2-stage thermal sequence, replace it with a single, continuous direct re-entry. 1 thermal event, 1 descent, no cooling and reheating cycle to trigger the gas pocket expansion. The fix addresses the identified mechanism directly and completely. It also means that every piece of flight-validated data for the Orion heat shield was generated under a re-entry profile that is now being deliberately abandoned. Every ArcJet test result, every thermal model calibration, every ablation rate measurement that fed into the simulation, predicting how AVCOAT will behave, all of it was built around a skip trajectory that the program has now decided not to use. The direct re-entry profile that Artemis II will execute on April 10th has never been flown. Not in an uncrewed test, not in a reduced-scale validation, not in any configuration that produces actual flight data at actual lunar return velocity under actual atmospheric entry conditions. The thermal environment that the AVCOAT will experience, the specific temperature ramp rate during the steeper direct descent, the peak heating duration, the spatial distribution of thermal load across a heat shield face that is now encountering a different aerodynamic flow field than the skip profile produced, has been modelled. It has not been measured. The model has not been validated. The validation is the flight. I want to be precise about what Charles Kamada has actually argued because his position is sometimes mischaracterized as simple opposition to the decision, when it is actually a more specific and more important critique than that. Kamada is not saying the direct re-entry is obviously more dangerous than the skip re-entry. He is not predicting failure. His argument is epistemological, and it goes like this. The confidence being expressed in the safety of the direct re-entry profile is not commensurate with the evidence base behind that confidence. We have mathematical confidence. The models predict that the direct re-entry eliminates the identified failure mode and produces acceptable thermal loads. What we do not have is empirical confidence, the validation of those predictions against actual flight data at actual conditions. And for any safety-critical system, the distinction between mathematical confidence and empirical confidence is not a philosophical preference. It is the operational difference between knowing something and believing something. The model that predicted the skip re-entry would produce no anomalous ablation was also believed to be correct. It produced 127. The model that now predicts the direct reentry will perform acceptably is derived from the same physical framework, calibrated against the same underlying test data, extended to a new set of conditions that the framework has never been validated against. The extension may be correct. The physics may transfer cleanly from the skip case to the direct case. The new thermal sequence may produce exactly the ablation pattern the model predicts. And the first time we will know whether any of that is true is when the capsule hits the entry interface on April 10th and the avcoat begins its controlled self-destruction in front of 4 living human beings. Kamada's concern echoes a pattern that appears in the history of human spaceflight with uncomfortable regularity. Before Challenger, engineers at Morton Thiokol had documented O-ring erosion on previous cold weather launches. The data existed. The anomaly was known. The decision was made through a process that prioritized schedule and applied pressure to the people raising concerns that the erosion was within acceptable risk. It was not. Before Columbia, the foam liberation from the external tank's bipod ramp had been observed on multiple previous flights. Each time, the orbiter survived. Each survival was treated as evidence that the risk was acceptable, rather than as evidence that the system was operating outside its design basis and getting away with it. The pattern in both cases was not malice, and it was not stupidity. It was the gradual normalization of an anomaly through repeated exposure without immediate catastrophic consequence, the drift of the acceptable risk threshold driven by the absence of a disaster that would have forced recalibration. The Artemis I heat shield anomaly sits in a pattern that has not yet declared itself. It may be exactly what the engineering response assumes: a diagnosed, understood, isolated manufacturing issue that the direct reentry profile will not trigger. That interpretation may be entirely correct, or it may be the first data point in a pattern of heat shield behaviour that our current models do not fully characterise, a pattern whose second data point arrives on April 10th. We do not know which interpretation is right. We will know on April 10th. The uncertainty is not in the engineering analysis. The uncertainty is in the gap between what the analysis predicts and what the physical reality will produce in conditions that have never been tested. Now let's talk about what reentry actually is, at a physical level, because Mach 32 is a number that sits in most people's minds as an impressive statistic and nothing more. The context transforms it from a number into something that earns genuine awe, the specific kind of awe that comes from understanding what is actually happening, not from being told it is impressive. The Concorde cruised at Mach 2. It was retired partly because the economics of supersonic commercial flight did not work, and partly because flying at Mach 2 creates a sonic boom that makes supersonic flight over populated land areas politically impossible. Mach 2 was considered remarkable. Military aircraft capable of Mach 3, the SR-71 Blackbird, the MiG-25, are legendary in aviation history, representing the absolute peak of sustained atmospheric flight performance achieved through decades of specialized engineering. Hypersonic research vehicles capable of reaching Mach 10 are at the current frontier of aerospace development, achievable in test conditions for brief periods after enormous investment. Mach 32 is not on this continuum. It is not a faster version of what those vehicles do. It is a different physical phenomenon entirely, governed by different equations, producing effects that do not appear at lower velocities and that cannot be understood by extrapolating from them. At Mach 32, the air in front of the capsule does not compress and heat in the way that air compresses and heats around a supersonic aircraft. The molecules do not have time for that. The kinetic energy of the encounter is deposited so rapidly, in the time it takes the capsule to travel its own diameter, the energy input to the air molecules exceeds what their molecular bonds can absorb through normal thermal mechanisms. The diatomic nitrogen and oxygen molecules that make up the atmosphere dissociate first. Their chemical bonds break under the energy input, splitting N2 and O2 into individual atoms. Then, at temperatures sufficient to ionize those atoms, electrons are stripped from their nuclei. The result is plasma, the fourth state of matter, the state in which matter exists as a mixture of freely moving electrons and positively charged ions interacting through electromagnetic forces, rather than through the chemical bonds that define solid, liquid, and gas. The temperature in the stagnation region directly in front of the heat shield, the point where the capsule's velocity is brought to zero relative to the surrounding atmosphere, exceeds 5,000 degrees Fahrenheit. That is hotter than the photosphere of the sun. the surface of the Sun. The capsule is not moving fast through air. It is generating a stellar plasma environment at its leading face and trusting 4 inches of ablative material to keep that environment from reaching the people behind it. The plasma sheath that forms around the entire capsule during peak heating is not just thermally extreme, it is electromagnetically opaque. The free electrons in the plasma, the same electrons that were stripped from atmospheric atoms by the energy of reentry, absorb and scatter radio waves across essentially all of the frequency bands used for spacecraft communication. For several minutes during peak heating, the Orion capsule is surrounded by a shell of ionized gas that no radio signal can penetrate in either direction. Mission control cannot transmit to the crew cannot transmit to mission control, telemetry stops, voice communication stops. The capsule disappears from the ground station displays as effectively as if it had ceased to exist, and mission control sits in silence, watching a clock waiting for the signal that will either resume or not resume when the plasma dissipates. During those minutes of blackout, the 4 crew members are alone with their instruments and with whatever the heat shield is doing on the other side of the capsule wall. Their monitoring systems are active. They can see the thermal readings from sensors embedded in the heat shield structure. They can watch the ablation rates. They can observe whether the temperatures at the structural interface, the boundary between the avcoat and the capsule hull, are tracking the predicted values or diverging from them. If the heat shield is performing as the model predicts, those numbers will be nominal, and when the plasma clears and the radio link re-establishes, the first transmission from the crew will be a confirmation that everything is fine. If the heat shield is not performing as the model predicts, if the direct re-entry thermal sequence is producing ablation behavior that the model did not capture, if the gas pockets that were not fully eliminated by the manufacturing changes are expanding in a new pattern under the new thermal load, the crew will know before anyone on the ground. They will know. They will be alone with that knowledge. And there will be nothing available to them that the physics of Mach 32 atmospheric re-entry does not permit, which is to say, there will be nothing. No abort procedure functions at those velocities and temperatures. No ejection system operates in that environment. The capsule is committed to the descent from the moment it hits the entry interface, and the descent resolves in one of 2 ways. The Apollo program validated its heat shield through a deliberate stage testing process that reflects exactly the kind of engineering discipline that the gap in Orion's test history highlights. Apollo 4 and Apollo 6 were uncrewed test flights specifically designed to validate the command module heat shield at lunar return velocity before any crew was placed inside it. The data from those flights fed directly into the confidence assessment for the crewed missions. By the time Neil Armstrong, Buzz Aldrin and Michael Collins splashed down from Apollo 11, the heat shield design had been physically tested at the actual conditions of lunar return re-entry. Not modelled, not analysed, tested. The Orion heat shield, in the direct re-entry configuration that Artemis II will use, has been modelled extensively. It has been analysed thoroughly. It has not been tested. The test is April 10th. Every other threat the crew has faced in the 72-hour window has been probabilistic, a thing that might happen with a calculable probability in a situation where the crew could potentially respond, shelter, adapt, and where the threat might simply not materialise. Re-entry is not probabilistic in that sense. It is certain. The plasma will form, the blackout will occur, the avcoat will begin its controlled self-destruction. And the material, carrying the same gas-trapping manufacturing risk that produced 127 anomalous locations on its only previous flight, now executing a re-entry profile it has never flown, at the end of a mission during which the spacecraft's electronics have been accumulating radiation stress for 18 consecutive days, will either fail correctly or it will not. At exactly the right rate, in exactly the right pattern, across exactly the right distribution of its face. The answer is already determined by the physics. The avcoat either has the gas pockets distributed in a pattern that the direct re-entry thermal sequence will or will not trigger. The material either has the ablation characteristics the model predicts, or it has characteristics the model has not captured. Those facts exist right now, fixed in the physical structure of the heat shield, waiting for April 10th to reveal them. Nobody on Earth will know the answer until the plasma decides to let them. Part 8. The 72-hour question. Let's draw every thread together now, because the picture that emerges from this entire analysis returns us, inevitably, to the question that has been accumulating since the moment 5 flashes appeared on the lunar surface and 2 trained astronauts went giddy at the sight of them. Everything we have covered, the radiation, the electron flux, the debris environment, the asteroid, the unmodelled comet, the heat shield with its anomalous history and its unvalidated new profile, all of it converges on the same 72-hour window, around the same 4 people, in the same capsule. And the question it asks is not really about them. It is about us, about what we know, what we think we know, and whether we are honest enough to tell the difference. Let's take stock of where we actually are. The crew of Artemis II has spent 18 days in an electron flux environment that exceeded the threshold for protective action in geostationary spacecraft for the entire duration of their mission, every single day, continuously, peaking at 6,075 particle flux units in electronics that are now carrying 18 days of accumulated charge stress that no pre-launch analysis fully characterized, because no pre-launch analysis was built around an 18-day continuous exceedance at that level. Those electronics are not broken, they are not alarming, they are functioning. But they are functioning in a condition that is measurably different from the condition they were in at launch, in ways that are difficult to fully quantify from the outside, in a spacecraft that is about to execute the most demanding phase of the entire mission. They witnessed, from 4,000 miles beyond the Moon, an impact rate on the lunar surface that does not reconcile cleanly with the baseline predictions from Earth-based monitoring programs, in a period when Earth's own fireball detection networks were running 4.5 standard deviations above the historical average. 2 independent data sources, one from the ground, one from 4 human eyes in the most remote location any person has ever occupied, both pointing in the same direction. Neither confirmed as evidence of a systemic debris increase, neither explained away by any analysis that has been published. They absorbed the effects of an M7.5 solar flare that arrived with 0 usable warning time, 8 minutes between ignition and arrival, against a shelter protocol that takes 1 hour in a solar environment that has been running above cycle predictions for the entire mission, from a solar cycle whose maximum was itself stronger than the model's forecast. They transited near Earth space during a week when an asteroid passed inside the Moon's orbit, as a sun-grazing comet threaded the solar corona on the same day as the flare, in a space weather environment that does not include sun-grazing comets in its operational forecast models. And they are now preparing to re-enter the atmosphere at Mach 32 on a trajectory profile that has never been tested with this heat shield design, using a heat shield that showed anomalous behavior in more than 100 locations on its only previous flight, and was subsequently redesigned for this exact re-entry. Each one of these facts, standing alone, is manageable. Each one has a monitoring system, a mitigation strategy, an engineering response, a probabilistic assessment that falls within some defined acceptable range. Taken together, in the same window, around the same crew, they form something that has no direct analogue in the history of human spaceflight. Not Apollo 13, not any shuttle mission, not any previous crewed lunar flight. This specific convergence, environmental, not mechanical, probabilistic, not catastrophic, simultaneous across multiple independent threat dimensions, is new. The Apollo 13 comparison is worth examining with genuine rigour, because it is the reference point everyone reaches for, and the differences are more instructive than the similarities. The Apollo 13 crew faced a single, specific, catastrophic mechanical failure. The oxygen tank 2 rupture in the service module, a failure that traced back through years of manufacturing decisions, ground handling anomalies, and design vulnerabilities that had been accumulating without anyone connecting the dots, cascaded through a system that had no redundancy for that exact combination of failures. 3 people nearly died. They did not die because the failure mode, once it occurred, was specific and diagnosable. There was a thing that had broken. The broken thing defined the problem defined the constraints, and within those constraints an extraordinary collaboration between 3 astronauts and a flight control team performing at the absolute peak of human capability found a solution that the mission designers had never anticipated needing. People called Apollo 13 a miracle, engineers called it a recoverable system failure. Both were right, and neither description fully captures what it actually was, which is a situation where the margin between 4 people dying and 3 people living was thinner than anyone in the room would have been comfortable acknowledging in advance. The lesson that got absorbed publicly was about human ingenuity. The lesson that should have been absorbed institutionally was about how thin margins get when systems are stressed in ways the models did not predict. Artemis II does not have a problem in the Apollo 13 sense. Nothing has broken, no alarm has sounded, no system has failed. The vehicle is performing nominally, and that fact that everything is working should not be mistaken for evidence that everything is fine. Because what Artemis II has is not a problem, it is an environment, and the difference between those two things is the difference between a situation that human ingenuity can address and a situation that human ingenuity is largely irrelevant to. You cannot solve an environment. You cannot improvise your way around solar maximum. You cannot fix 18 days of electron flux accumulation by rewiring a circuit. You cannot navigate around a debris population that cannot be precisely characterized in a spacecraft on a fixed trajectory that cannot be shortened. You cannot add validation data to a heat shield's test history while it is in the middle of its first crewed flight. The threats the crew is facing are not failures of engineering that smart people can work around. They are properties of the universe operating at or above the range that the mission was designed for, in ways that the models that informed the mission design did not fully predict. The crew's job is not to fix anything. It is to keep everything functioning until the Earth's atmosphere takes over, until the physics of reentry become the dominant reality and the probabilistic threats of deep space stop mattering, and then to survive the reentry. That is what they are doing, and it deserves acknowledgement that goes beyond the clinical language of risk matrices and probability assessments, because the human reality of what Reed Wiseman, Victor Glover, Christina Koch and Jeremy Hansen are doing right now is extraordinary in a way that statistics cannot capture. These are people who trained for years, who understood in specific and technical detail what the risks of this mission were when they accepted the assignment, who sat on top of the most powerful operational rocket ever launched and rode it away from everything that has ever been called home, who watched the moon get hit by kiloton-scale explosions and responded with giddiness, the particular giddiness of people who have made a complete and unconditional peace with the fact that their profession puts them in the presence of things that should not be survivable. They are not victims of risks they did not understand. They are professionals who understood the risks and flew anyway. That is what exploration has always required of the people willing to do it. But the question that will matter after the splashdown, after the photographs and the headlines, and the justified celebration of an extraordinary human achievement, is the institutional question, the quiet question, the one that does not get asked at the press conference but gets asked in the meeting room 2 weeks later, when the post-flight data is on the table and the people responsible for the next mission are in the room. Did we know what we were committing them to? Not in the general sense. Everyone knows human lunar missions are dangerous. The question is specific. Did the mission architecture adequately account for the solar activity level that Solar Cycle 25 maximum was actually producing, rather than the level that the models predicted before it exceeded those predictions? Did the debris environment modelling accurately represent the near-Earth space environment in Q1 2026, given what the ground-based fireball networks were measuring and what the crew subsequently observed? Did the decision to modify the re-entry profile to a direct entry, a profile with no flight-validated data behind it, reflect a full and honest accounting of the uncertainty that absence of validation introduces? Did the electron flux exposure duration fall within the design assumptions for Orion's electronics? And if it exceeded those assumptions, were the exceedances formally documented and accepted by the decision-makers responsible for crew safety? These are not hostile questions. They are not questions that assign blame or assume bad faith. They are the questions that a functional, honest risk management culture asks as a matter of institutional discipline before the mission launches, as part of the process by which human beings take responsibility for committing other human beings to environments that can kill them. The Rogers Commission asked versions of these questions after Challenger. The Columbia Accident Investigation Board asked versions of these questions after Columbia. In both cases, the answers revealed not that individual engineers had made obviously wrong decisions, but that institutional processes had normalized the accumulation of unresolved anomalies until the accumulated weight of them produced a catastrophic outcome that, in retrospect, was visible in the data if anyone had been asking the right questions. The foam strike that destroyed Columbia had been observed on dozens of previous flights. Each time it was assessed, documented and accepted as within tolerable risk because the previous flights had survived it. The O-ring erosion that destroyed Challenger had been measured and recorded in previous cold weather launches. The engineers who were alarmed by it were overruled by an institutional process that had been normalizing the anomaly for years. The pattern, in both cases, was not ignorance. It was the gradual drift of acceptable risk thresholds driven by the absence of immediate catastrophic consequences. We did this before and nothing bad happened, therefore the risk is acceptable. That logic works until it doesn't, and when it stops working in front of the whole world. The Artemis I heat shield anomaly, 127 unexpected charring locations on the first and only test flight of the system, is a data point that has not yet declared what pattern it belongs to. It may be exactly what NASA's analysis says it is, a diagnosed, understood, corrected manufacturing issue that the redesigned direct reentry profile will not reproduce. That is the most optimistic interpretation, and it may be correct. Or it may be the first data point in a pattern of heat shield behaviour that the current models do not fully capture, a pattern whose second data point will be written on April 10th at Mach 32, with 4 people inside. We do not know which of those interpretations is right. We will know on April 10th. Or we will know that neither interpretation was quite right, and that the heat shield behaviour in the direct reentry profile is different from both what the skip reentry produced and what the direct reentry model predicted. Here is what makes this moment in the Artemis program particularly consequential, beyond the immediate mission. Artemis III is already in planning. Artemis III will land humans on the Moon. It will involve a lunar surface stay, longer exposure outside the magnetosphere, more transit time through the deep space radiation environment, more time in the debris field. A second crewed re-entry using the same heat shield design, now with the direct re-entry profile that Artemis II will have validated, or not validated, on April 10th. The lessons drawn from Artemis II will directly shape the risk assumptions embedded in Artemis III. And lessons drawn from a mission that succeeded can be the most dangerous lessons of all, if the success obscures the question of why it succeeded. A capsule in the Pacific Ocean with 4 healthy crew members looks identical, regardless of whether the mission succeeded, because every margin held comfortably within its design basis, or because every margin held narrowly, at the edge of its design basis, in an environment that was running above the predicted range. The photographs look the same, the headlines read the same, the celebration is the same. The difference lives entirely in the data, in the post-flight analysis that compares what the environment actually was to what the models said it would be, and asks honestly whether the gap between those two things was within acceptable uncertainty, or whether the mission succeeded in spite of conditions that exceeded the design assumptions. The history of exploration, not just spaceflight but all exploration, is full of voyages that came back successfully from environments that were more demanding than the ships were designed for. Some of those voyages produced honest lessons about where the margins actually were, and the next ships were built better. Some of them produced the conclusion that the ships were adequate, and the next voyage pushed further into the same environment with the same margins, until eventually a voyage did not come back. The difference between those two outcomes was not the quality of the engineering. It was the honesty of the question asked after the successful voyage. The crew of Artemis II watched our star disappear behind the Moon from a place no human being had ever been. They saw the universe performing its oldest, most indifferent physics in real time, on a surface that has been recording those impacts for 4 billion years. They flew farther from Earth than anyone since the Apollo program ended, more than 50 years ago, in a spacecraft built by thousands of people who gave years of their lives trying to anticipate every way it could fail. They did all of this during a solar maximum that exceeded predictions, through a debris environment that raised unresolved questions, beside an asteroid that passed inside the Moon's orbit, past a comet that threaded the corona on the same day the Sun fired a near X-class flare at them with 8 minutes of warning, carrying 18 days of radiation stress in their electronics toward a heat shield that has one anomalous flight behind it and one critical one ahead. If they make it home, and every person who has worked on this mission wants them home, with an intensity that does not translate into any professional language, we will call it a success. We should call it a success. It will be a success. But the real question is not whether they made it. The real question is what we learn from how they made it, and whether the institutions responsible for the next crew are honest enough, rigorous enough, and humble enough in the face of an environment that does not negotiate and does not grade on a curve, to tell the difference between a system that was ready for what it encountered and a system that encountered more than it was designed for and survived anyway. because the universe is not keeping score of our confidence, it is keeping score of our margins, and the next crew is already training.